Section 2-8 is on graphing linear and absolute value inequalities. A linear inequality is similar to a linear equation, but it has an inequality sign. A less than or equal to, a greater than or equal to, or a greater than. Its graph is a solid or a dashed line with one side of the line shaded. And you'll probably recall from Algebra 1, it's a solid line if it's a less than or equal to, or a greater than or equal to, and it's a dashed line if it's just a less than or a greater than. And then when it comes to shading one side of the line, one way you can do it is to test a point, usually the origin, if the line doesn't go through the origin, or if you've written the line in basically what is y equals mx plus b form, then if it's a less than, you're going to shade below the line. If it's a greater than, you're going to shade above the line. Let's take a look at an example. Here we have the linear inequality, 3x plus 1/2 y is less than 2. First thing I want to do is rewrite it so it looks like y equals mx plus b. Basically solve it for y. To do that, I'll start by subtracting 3x on both sides. So 1/2 y is less than negative 3x plus 2. And then to get rid of that 1/2, I'll multiply everything by 2. And that gives me y is less than negative 6x plus 4. So since it's just a less than and not a less than or equal to, my line is going to be dashed. And because it's a less than, I'm going to be shading below the line. So let's go ahead and graph that line. My y-intercept is 4, and my slope is negative 6. So I'll just give myself a few dots here on the line, and then fill in between those dots with dashes. And my shading is going to be below the line, which is a little tricky here because this line is almost vertical. It has a very steep negative slope. So what you want to look for is where is the y-axis below the line. And so that would be over on this side, which looks a little bit more like the left side of the line. But we want to shade everywhere where the y-axis is below the line. And so that would be over here. Now remember what this means is that every point in this shaded region works in this inequality, and every point in the unshaded region does not work. Let's just try one for fun here. Let's try 0, 0. So when I plug in 0 for x and 0 for y, I'm going to get a positive 4 on the right-hand side and a 0 over here. So that is true. 0 is indeed less than a positive 4. If I were to choose the point, let's say 1, 1, over on the unshaded side and plug that in, that's going to give me a negative 2 on the right and a 1 on the left, and 1 is not less than negative 2, so that makes sense that the right-hand side is not shaded. Let's take a look at an absolute value inequality. So this is going to be basically the graph of an absolute value function. So that's going to be in the shape of a V. It's going to be solid or dashed and then shaded either above or below, and generally above is going to be inside the V and below is going to be outside the V. In order to do this, I'm going to solve this for y by dividing everything by 2. So that gives me y is greater than or equal to, and I'm going to put that divided by 2 out front as a times 1/2. So y is greater than or equal to 1/2 times the absolute value of x plus 3. So this is going to be a solid line because it's an or equal to, and I'll be shading above or actually inside the v. In order to graph this, I'm going to make a table of values. And if you'll recall from the last lesson, we want to find what is the x-coordinate of our vertex. To do that, I want the stuff inside here to be equal to 0. So when x is negative 3, it gives me a 0 inside the absolute value bars and a y value of 0. Now that 1/2 out front is a little bit of a bother because I don't really want to go to fraction land. I would like to have even numbers that I'm taking the absolute value of so that when I divide them by 2, I actually get a whole number. So let's try something like, since negative 3 worked, let's try negative 5. Negative 5 is going to give me a negative 2. Take the absolute value of that for a positive 2 times 1/2 gives me a 1. That worked great. So let's try negative 7, negative 1, and 1. So negative 7 gives me a negative 4. The absolute value of that is 4. Divided by 2 is 2. Negative 1 gives me a 2. Absolute value is 2. Divided by 2 is a 1. 1 gives me a 4. Absolute value is 4. Divided by 2 is a 2. That looks pretty nice. Let's plot those points. Negative 3, 0, negative 1, 1, 1, 2, negative 5, 1, and negative 7, 1. This is a solid line, so I'll go ahead and draw the solid line here. And since it's a greater than, I want to know where is the y-axis above the graph, and that's going to be inside the V here, so I'm going to shade everything inside the V. And remember again, that means every point inside there will work in this inequality. And actually looking at just the graph of the V kind of makes sense from what we learned in the last lesson on transformations of some of our parent functions. The parent function of this is the absolute value V, which is centered at the origin and has a slope of 1 and a slope of negative 1. Notice this has been translated 3 units to the left because that's the same as x minus a negative 3. And this 1/2 out front actually makes my graph a little bit wider. It actually expands the graph a little bit. So in this lesson, we took a look at linear and absolute value inequalities. We graphed the line, or the absolute value V. We made it solid or dashed, and then we shaded one side of the line or the other, or inside the V or outside of the V.